Okay, let's look at one of the easier one of the easier series now, P series. We like this series because it's very easy to tell if it converges or diverges right away. So P series typically has the form 1 over n to the p. Do not confuse this with the geometric series where you have r to the n. It's geometric. And P series is n to the p. So I can't stress enough how important it is to be able to differentiate between the two. A P series is the variable to a number. A geometric series is a number to the variable. You have to approach them differently. Now, a P series converges if P is greater than 1. It's that easy. Else, it diverges. Okay, so let's look at a few examples. Okay. So in this case, P is equal to 1. This is n to the first. P is equal to 1, therefore diverges. That fast. Now this is a P series, but it's also a special one. It's got a special name. We call this the harmonic series. But that's not all that important. You just have to know that it diverges. Let's look at another example. So this isn't written in the right form yet. It needs to be 1 over n to the p. So we'll rewrite this. N equals 1. This becomes 1 over n squared. Our p is 2, which is greater than 1. Therefore, we converge. Let's look at another example. Cube root of n to the negative second. This can be rewritten as n to the negative 2/3, which can be rewritten. Remember, we're looking for 1 over n to the p. So we'll rewrite it until we get there. So 1 over n to 2/3. So you see p is 2/3, which is not greater than 1. Therefore, the series diverges. So don't forget all your algebra skills. So you can see by the divergence test why this is going to diverge, because the limit is 2. But we'll try it with a p-test as well. So we can rewrite this as n squared over n cubed plus 2n cubed over n cubed. This is now 2 series. A series of 1 over n plus a series of 2. So this diverges because it's a harmonic. And this diverges, of course, because you're adding up 2 infinite times. Just 2 plus 2 plus 2 Obviously that never converges. Therefore, our series diverges. Okay, another example. Okay. So we'll rewrite this. This is n to the 1/2 divided by n to the 1/3. Remember that you subtract exponents when you divide numbers at the same base, so this becomes n to the 1/2 minus 1/3. So let's see, 1/2 is 3/6. 1/3 is 2/6. So this just becomes 1/6. So this is equal to n to the 1/6. Well, actually, this isn't really a p-series. It is, but it's fairly easy to see that this diverges. It's just going to get bigger and bigger. I was thinking it was something more like cube root of n divided by the square root of n. And this is going to be equal to n to the, this is backwards, so it'll be 1/3 minus 1/2, which is negative 1/6. We'll rewrite this in the p form. 1 over n to the 1/6. You see our p value is 1/6, which is not greater than 1. Therefore, diverge. Okay. Go to another example. So, rewriting this becomes 57 over n to the pi. Here our p value is pi. Pi is greater than 1. Therefore, our series converges. Okay, one more. Okay, so I'm going to clean this up a bit. In the numerator, this becomes n to the 22nd divided by n to the 32nd, which is equal to n to the 22 minus 32 is negative 10, which is of course equal to 1 over n to the 10. See, our p value is 10, which is greater than 1. Therefore, we converge.